So I was discussing about the reinforcement learning. Okay. These probability concepts, maybe I told you that I hope you all are aware, no? This probability expectation, this probability density functions, probability mass functions, this you all know. And these are the distributions, the probability density functions, some of the, the popularly used density functions, some of the popularly used mass functions, and this is the distribution, value into the probability, this is the expectation basically. Then some properties of the expectations. Yeah, and then we discussed about the Markov decision process also, because the RL is basically a Markov decision process. So the Markov decision process is having this kind of tuple. There is a state, S is the set of possible states, A is the set of possible actions, then there is a reward function, transition probability, and also the discount factor. Okay, so these are the different components of the MDP. Okay, so we will need these in order to define a RL also. We need to have a set of states, we need to have a set of actions, a reward function, transition probability, and also a discount factor. So in the last class we discussed about the importance of the discount factor, and these examples we have seen. Okay, so now let me directly today go to the algorithm, the DQN. Okay, so this is our Q table. So now you know that once we can get the Q table, then it is very easy for us to determine the action. So the algorithm is, if you are following a greedy algorithm, then you have to select, given a state, you have to select the particular action which is have the highest Q value. Okay, so Q is a quantification. So the Q value will give you the goodness of a particular action given a state. So if this matrix is optimal, once you have a optimal matrix, so given a state, you only have to apply the argmax, and you will be able to select the particular action which has the highest Q value. So your task is to get the optimal Q matrix, and then you are done. So you are in a particular state. Now you apply the argmax and you select the action which is having the highest Q value. So that is the idea. Now let me show you this one. A role of discount factor that I have shown you, and exploration exploitation that also I have shown you. Some applications, this dialogue I have shown you. So let me show you so this tabular methods and the Q network. So today let me directly go. Okay, so these are the various reinforcement learning algorithms. Okay, so if you have to categorize RL algorithms, we have some model free RL. So there are some value based RL like double DQN, Q learning, double DQN, dwelling DQN. These are some value based RL. Okay, so where we are optimizing the value function, so either the Q value function or the V value function. So by optimizing the value function, we are getting the policy. Like we are not directly optimizing the policy, but we are optimizing the value function, and that way we are getting the optimal policy. And these are some policy based RL. Okay, so where we are directly optimizing the policy, like we are directly getting the optimal action given the state. So like that the state transition, there is no value function or the Q function, we are directly getting the optimal action. Then there are some model based RL. Okay, like this, that learn the model, this I2A, MBVA, alpha 0. So these are also there. Today I will discuss about some value based RL and also some policy based RL. Okay, so in the value based RL, we are trying to find out the optimal value of this Q. So as I mentioned already that this Q is the kind of quantification. So given a particular state and the action A, so it will give you it will basically try to quantify the goodness of a particular action given a state. So I mentioned to you like in terms of these dialogue systems. So when the chatbot is saying something, giving a response, so whether the response is relevant or in context. So based on this, we can give a reward. No, I discussed about the reward yesterday. I showed you some examples of the reward, like when the chatbot is asking something. If suppose there are some important slots, and if the chatbot is asking some relevant question by which you can fill some important slot, then that means that it is relevant. So that way you can quantify the goodness of the response. So you can extract the important slots from the user's utterance, and then accordingly you can calculate the reward. So reward is a very important signal in case of reinforcement learning, because that is the only supervision that you are giving, to the agent. We don't have any class level and etc. So this is the only feedback that you are giving to the agent. So you have to carefully design the reward, and when you are designing any RL based reinforcement learning based agent or reinforcement learning based system, that is the most important part, how to design a good reward function. And there is no such well defined formula. So it is a trial and error system. So like what I mentioned in our work on dialogue systems, it was a trial and error method. So we tried different ways of defining the reward. Sometimes there is a convergence, sometimes there is no convergence. So there are, you have seen there are many parameters, no, W1, W2. So what will be the values of these parameters? So, you have to empirically, you have to set those parameters. So there is no guidelines to decide the reward function. Based on the problem statement, you have to analyze it, and then you have to define your reward function. Yeah, so I will discuss about this DQN and DDQN, which are value based RL, where we will be mostly optimizing the Q function. And then there are some policy where we are directly optimizing the pi, means we will get the action directly from the state. There is no value or Q function there. And then there are also some model based RL. Yeah, so you can see that in value based so policy is basically this state to action mapping, like in our finite state automata. So given a state, what will be the optimal action, or what will be the next state? So that is the kind of policy pi. So like given a state, what will be the optimal action? So that you have to search, no? That is the optimal policy I am talking about. So in RL, we want to find out the optimal policy, that when I am in a particular state, what is the optimal action? What is the best action? Yes, it's a good question. So sometimes it's deterministic, sometimes non-deterministic also. So like in some cases, like it is a stochastic process. So there is also probability. So there is a probability involved in taking a particular action. So it's not always, that it is always one, with one probability you are taking an action. So you can have probability associated with each action. So we are basically talking about the optimal, the action. Like when in a particular, like I talked about this, this mini games, no? Like for example, tic-tac-toe. You are suppose you are playing the tic-tac-toe. So in a particular position. So now where to put X. So you need a particular action. So when you are in a particular state, where to put X. So that optimal action is determined by the policy.
a value for the function Q S of A.
Yeah, so this value function will give you the whether the state is good or bad. So you suppose in a game you somehow reached a particular state. So now whether this state is good or bad. So that is determined by the the value function. Because there are so many states, no, it's a huge search space. So you have to discuss some states. When you are searching for the optimal policy, you need to discuss some states also.
What is the difference among policy and value based?
Oh, okay. So here in this.
Yeah, like value and policy also state is left to action.
Okay. This you will understand when I will discuss about the algorithm. That time you will understand. But if policy is this. So policy is basically the mapping from S to A, and the value is basically the algorithm you will understand. So directly I will come to that. So that time you will understand the algorithm. So how it is directly optimizing this so basically this is the thing. See, so policy is this. So based on the policy only you are deciding A. So you are applying pi is the policy, and pi based on the policy you are selecting A. Okay, and this is the optimal policy. So pi star is the optimal policy, and based on the optimal policy you are deciding the optimal action. Okay, this algorithm you will understand. I will discuss. Yeah, so so basically you see here what is happening. You see this picture. So here in case of the value based DRL, we are giving the state and the action. So input is the state and the action, but in the output we are approximating the Q value. Okay, see this picture. So here there is a neural network. So this neural network is simply approximating the Q value. It is not, but in case of policy based DRL, there is no concept of Q value or the value V. Okay, it will simply take the input, the state, and then it will give you directly the output action. So what is the optimal action A? So it will know there is no consideration of Q or the V. That is the only difference. But now in case of value, there is a concept of Q and the V.
So in value based, for each state, all the actions are checked, which is the best action.
No, so in value based, we are also quantifying this, the goodness of the state. Like we have the value function for each state. But in policy, this value function doesn't exist. It is directly mapping from state to action, like our final state automata. In final state automata, we used to go from one state to the another state. There was no value, some value function or Q function, no. Very similar to this, but here in value based DRL, now we are also quantifying the goodness of a particular state. So in a value based RL, we learn a state action or value function. The agent is expecting a long term return of the current state and the policy pi. Okay, so basically you know that this Q is recursively defined. It is the what? Cumulative. We have defined what is this? Expected cumulative reward. And you have to consider all the future rewards also. Not only the immediate reward, all the future rewards also. In a policy based RL method, we try to come up with such a policy that the action performed in every state helps you to gain maximum reward in the future. So now let us see the Q learning. Okay, so how the Q learning works. So Q learning is a basic form of RL which uses the Q values to iteratively improve the behavior of the learning algorithm. So initially you can initialize your matrix with some random values. You have a matrix, Q matrix, you initialize with a very random values. Okay. So now, so basically it is a model free. So now this is the equation which is very important to update the Q values. So you have some initial values. So this is the old value, okay. So this is the old value, so it is a iterative process. Like in K-means also it was iterative process. We had the initial set of centers, then we kept on updating the centers, no. So similarly here also we will initialize the centers with some, we will initialize the matrix with some random values, and then we will keep on updating those values. So here also you can see that there are some old values, and then we are updating them. So this learning rate, you know that in neural network always there is a learning rate, no. We always want to control like how much you want to update. It's not exactly that there is a difference in the old value and the new value, but we are not updating with the exactly with the error. So there is a learning rate, so that alpha is the learning rate. And now see, so this is the thing that this is now the immediate reward, discount factor, and the estimate of the optimal future value, okay. So this is the new value, okay, and this is the old value. So this is called the temporal difference. So you are proceeding one step further. So basically you in a timestamp, so you are proceeding one step further. You are proceeding like you are going to a new state. So you now know the immediate reward also. So you are adding the immediate reward and the Q value of the next state. So that way you are getting a approximation, you know, getting a new value, you are approximating a value, and from the table you are getting a old value. So this temporal difference, so this is why this is called temporal difference, because you are in a timestamp, you are going further ahead. There is a state change. You are in a ST, now you are going to ST plus 1, okay. So this is a very important, this is also called the Bellman equation, okay. This temporal difference formula is very, very important, and this is also used in DQN, in deep Q network we will see, and this is used to update this matrix. So this is used to update the matrix, okay. So you know that this you already know that we have the states. The state S represents the current position of the agent in an environment. Action, the action A is the step taken by the agent when it is in a particular state. Rewards, for every action the agent will get a positive or the negative reward. Episodes, when an agent ends up in a terminating state and can't take a new action. Q value used to determine how good an action A taken at a particular state. Temporal difference, a formula used to find the Q value by using the value of current state and action and previous state and action, okay. So yeah, so basically you are following this, you are following the policy and taking the action. Okay, so this is the Q learning. You initialize with a very either with value 0 or with any value. You can initialize. You select an action to perform. You perform the selected action. This reward you have to get, okay. This reward function you have to design. This reward you have to somehow, there must be some, you know, mechanism. Either you have to design your own reward function. So this reward you have to get from the environment. Like you have to have your own reward function to evaluate the action. And then by using the temporal difference formula, what just now I have shown, that is the Bellman equation, you have to update the Q value, Q table, okay. So you have to update the Q table. So that is the idea. So you keep on doing like this. So and this is the iterative process. So this is the Q learning, that you initialize the Q arbitrarily, repeat for each episode. You initialize, you start with any state. You can start with any state. Now for each step in the episode, you select you know A. Now you apply the greedy algorithm. You select the action which is having the highest Q value from A using the policy derived from Q. Take an action A, observe R and S. So like what is the immediate reward, what is the next state. so that you have to do as per the policy. Then you have, this is the temporal difference formula. This is the the estimated Q value. This is the old Q value. Okay, this is the estimated and then you update until S is terminal. Yeah, so this way that we are updating. So here you can see that, for example, these are our these are our states: start, ideal, wrong action, correct action, end, and these are our actions: fetching, sitting, running, and we are keep on updating the Q table and initialize with 0, and then maybe we are getting a final Q table like this.
Ma'am, so when you interpret that this Q table is actually the representation of that finite automatic state action.
Yeah, so yeah, but now you have this value also, like this is a Q value is a quantification. Yeah, so like in finite state automata you have only state to state transitions, no? State
What
to,
about then a graph kind of thing with weights?
yeah.
State transitions.
Yeah, so like you have now this kind of weights. Yeah, so you know that the discount factor determines the importance of the future reward, that you know. So like if this gamma is 0, we'll make the agent myopic or short-sighted by only considering current reward. No, like if you will make the discount factor equal to 0, then it will simply focus on the immediate reward. It will ignore all the future rewards. Then there will be no impact of all the future rewards. And if gamma equal to 1, then it will give equal importance to all the rewards. So you will make it strive for a long-term high reward. So both are not good. So we have to keep a value between 0 to 1.
Ma'am, so like if we talk about if we draw an analogy from the learning rate kind of thing, so like if learning rate is 0, it does not convert. And like it takes infinite time to convert. And if learning rate is too high, it would never convert. So
True.
like, how can we draw like myopic would not converge or
so myopic means though it is then only immediate reward. So then so there is no flavor of RL at all. No, it is a kind of, you are simply seeing what is the immediate reward and accordingly you are doing, and I have shown you like then it may get stuck at local optima, like you will not be able to see reach the goal at all. And if you are giving equal importance to all the future rewards, then somehow you are also ignoring the current state. Like current state should obviously have the higher impact. So yeah, it's very difficult. So like what we are doing is that we are simply keep on changing this gamma value, and then we are checking this kind of convergence. So yeah, so I think this TS will show you how to change these values. But yeah, similar to learning rate also, it's a parameter. You have to do the sensitivity study of this gamma. Yeah, so now similar to this, you know that this was our tabular Q learning. So we are doing what? That we have a big table. Just imagine that tabular Q learning is okay. But just imagine if you have a large number of states and a large number of actions, how big your Q table will be. So you have to maintain such a big Q table, and you have to update all the entries of the Q table. So it is very difficult. No, every time you have to update the Q table, and maintaining the Q table will be very difficult. So tabular Q learning was very popular, but then people realized that as deep learning is there, and or the neural network is a good function approximator, so can't we use deep learning or the neural network to approximate the Q value? So that is the idea. You know that the neural network can easily be used as a function approximator. So can we use a neural network as a function approximator? Can it approximate the Q value? So that is the idea, that now we will be giving the input, the state in the input, and there will be a neural network and there are multiple layers, and in the output we want to get the approximated Q values for different actions. So it's a kind of a, the regression task. It is not a classification task. So we want, like a maybe there will be multiple neurons. There are multiple neurons for different actions. There will be one neuron, and it will give us the Q value of different actions. So that is the deep Q learning. Yeah, so you know that why deep reinforcement learning, you understand that there is much advancement in the deep learning and also advancements in reinforcement learning and the advancements in computational capability also. We have now the GPU capabilities. And yeah, and also we can do the end-to-end training. So that is also another advantage. So that's why, the deep Q learning is now introduced. Yeah, so basically, you know that reward function is basically a kind of a signal, okay, and reward is giving us the kind of a signal that which states and the actions are better. For example, when you are designing a driverless car, if it is running smoothly, then obviously you have to give high reward. But if there is a collision, then you have to give a penalty. So in that way you have to analyze all the situations, and accordingly you have to design your reward functions. And you know that I have already mentioned to you that this nowadays this DQN is applied everywhere. Not people are not using the tabular Q learning, but people are mostly using the DQN only. Not only DQN, DDQN. I will show you that DQN is also having some disadvantage, because there is only one neural network which is used to calculate the old value and also the new value. So that is a problem. So there is DDQN and also dual DQN. So yeah, but mostly in almost all the applications like autonomous driving, language and dialogue, finance, Atari games, real world robots, everywhere people are applying this deep RL only. Okay, so this is the overall idea. So basically, you know that we are using the neural network as a function approximator. So we will be giving the state, and we are expecting, that what is this Q value. So Q value is a function. If we give a state and the action, we can easily calculate the Q value. So now you know this deep Q network is used as a function approximator. So we can give the input the state, and in the output we can get the Q values for different actions. So you know that these are the initially in case of tabular Q learning, this was the thing that we initialized our Q table, then we selected an action, and then we updated the Q table using that temporal difference formula. So now also we will be using the same temporal difference formula, but now this temporal difference formula will be our error. Like you know that in back propagation, what we have done, we need a error, no? If you want to back propagate some, you want to update the network, like you can initialize the weights of the network with some random values, but you have to update the network. So you need to backpropagate some error. But here what is the error? You don't have any supervised data. Like in general, in normal in perceptron or in normal feed forward neural network, what you need? What is your error? Yeah, the actual output minus the predicted output. That square error used to calculate. But here we don't know the actual Q value. Do you know? We don't know the actual Q value. We can only approximate the Q value, but we don't know the actual Q value. So we can only calculate the temporal difference. Okay. So that is the idea. The same formula we will be using like our tabular Q learning, the temporal difference formula, and that will be the error. Okay, our objective is that over the time when there will be a convergence, this temporal difference error will diminish. So when there will be a convergence, finally there will be zero temporal difference error, and this error will try to backpropagate to update the.
Ma'am, so the neural network is like a simple feed forward or
No, it is now a simple feed forward.
but then like we need like for the first feed forward we need to wait, then only we could successively count the next feed. We are depending on the very previous state itself.
Yeah, so basically now, no, like here you see, so no, but like your state is in the input, and you are assuming that your neural network is approximating the Q value. Okay, so you are what you are doing, I will show you. So basically your neural network is giving you a Q value, and so what is happening is that, see, so you are in a particular state. So for this particular state you invoke the neural network and you get a Q value. Okay, now given this particular state, you know that what is the you know that this is your optimal action, and this is the reward, and this is the new state. So for that new state you can again use the same network to get the Q value. So you have that Bellman equation, R plus the next state Q value. So that will be your like new Q value, and you have the old Q value. So that is the difference. You understood? So the same network is used. That is the problem with DQN, that the same network is used to approximate the Q value of the S and also the Q value of the S dash. But now I will show you how to simulate the data for training this DQN, because we need this kind of tuple, no, S, A, S dash, R. So this tuple we have to somehow generate. Yeah. So somehow we have to, what we have to do is that we have to simulate an environment, and by simulating the environment we have to generate some training data for training this DQN. So now I will show you how to simulate this. So this is the idea. You can see that initially we have this kind of Q table. So in case of Q table it was very easy, like for example, if you want to see the value of this Q31, it means the state 3 and the action 1. So you can easily go to this, so here you can easily go to the state 3 and the action 1, and you can easily go get the corresponding Q value. And now what is happening is that if you want to use this DQN, then you have to use the state 3 as the input, and there are in the output there are 2 neurons, one for action A0, another for action A1, and the action A0 will give you the Q value for action A0, and the neuron A1 will give you the Q value for action A1. So you will be getting the same value, but in a different ways. Okay. So this is a comparative study how we can use the Q table and how we can use the DQN. Yeah, so this is the thing that every time that we have to like we can use the Q table, the DQN, but for training the DQN we need the world, because this temporal difference formula can only be used with the help of the environment, because we need the immediate reward. If you see the temporal difference formula, in the temporal difference formula we have the immediate reward. No, see, this is the immediate reward, and this immediate reward is coming from the environment only. So this may be this Q value you can approximate from the network. This Q value also you can approximate from the network, but in order to understand the R, you need the help of the environment. So that's why somehow environmental help is necessary. So that I will now show you. Yeah, so what are the okay, so there is a component called the environmental simulator, okay. So there is a component called the experience replay. So this experience replay basically interacts with the environment, and they generate the data for training the Q network, okay. So yeah.
While doing the other one for I think Q table, it said that the action was selected based on the Q table, right? If you always select the maximum action, then the other action won't get it.
Okay, so then yeah, that is the like I told you that this is giving you a Q value. So finally you have these two options. So I mentioned the exploration, exploitation. So either you can apply the greedy, like you have two probabilities. I mentioned there was a slide. So either you can use the greedy based approach, like based on the Q value you can select the action, or you can select any action. So these two also have some probability. Sometimes when you are exploring, when you are picking up some action, sometimes you go for the greedy, like select action based on the highest Q value, or sometimes randomly pick any action.
And one more question. In an episode, if the same state is encountered twice, will the Q value change?
Same state will encounter twice.
Like the situation, like the number of steps before in the history, or does any of this affect the Q value while updating?
Yeah, I think it will change. Yeah.
So which term would change?
So where is the confusion? Okay, no. No? Okay. Sorry. Okay, this one. Okay, this one I have to use. No, where is the slide? Okay. Now this one, no? Okay, here. Which one may tell me? For each step of episode. So the episode is okay. So here you were saying which one?
Yeah, so if we are choosing the action as from the policy derived from you,
Huh.
you said you already correct and told me about it. My question is, if the same state is encountered twice,
Huh.
like if the Q value is the same,
Huh.
I could start filling the Q values in an ordered fashion, so I don't have to choose the step in an episode, right?
So you mean to say that you will not update?
No, like I'm asking whether the history would affect the Q value and which term changes that.
Yeah, because I think till the convergence, the Q value will keep on updated. Because I don't think that your table will, if there is no convergence, till now it will not match. This temporal difference formula, this temporal difference will not be 0 till the convergence. So whatever you will get from the immediate reward plus
Immediate
the
reward would remain the same when the state and an action, like the pair would remain the same. Right? Only the Q S dash minus A dash minus Q S A would change.
Q is dash, yeah, because you are keep on updating. You are keep on updating. So yeah, so in a episode you meant to say that in between there is no other update.
S dash is the current state, S is the next state.
Yeah.
The other way around.
So but reward function you can't say that it is fixed.
No, like given a state and an action, the immediate reward remains the same.
No, not always. It depends on the nature. No, it depends on the nature. Like in our case, like the dialogue system I gave you, no, it's not like in case of if it is plus, if you are giving a +1 -1 reward, then it is fixed. But if it is in terms of some other variable, like I showed you in the last class, like it is in terms of what is in the slot, that there is a global array, no, what are the entries of the array. So that is in terms of the entries in the slot. So and that entries keep on getting updated. So it may vary. So because initially maybe there is less entry, so the reward would be less. But when you are very near to the goal state, it will get higher reward. So it depends on the reward function, how you are designing. Okay, so basically this experience replay memory is very important because it is interacting with the environment to generate data to train the Q network. Okay. So yeah, so basically initially I will talk about this Q neural network, but as I mentioned that there is this DDQN also, and this DDQN uses two network, Q neural network, and also there is a target neural network. Okay, because you have seen that we need two Q values, no, one Q value for S, another Q value for the S dash. And obviously if you are using the same network for approximating Q and Q dash, that is a kind of bias, or maybe that is not good. So that's why maybe we can use the two separate networks. That is the idea of DDQN. Okay, so this is the thing. I also have a illustration. So maybe I can show you first this. So what it is doing, experience replay. So it is picking any random action. So it is starting with any random state, okay, and it is picking any random action, and then environmental simulator is somehow invoked or it is consulted, and accordingly it is getting the next state and the reward, okay, and this tuple, the current state, action, reward, and the next state, this tuple is stored in a array or in a somehow in a memory. Okay, and this is called the experience replay memory. So, and this is your kind of a training data. So, this is your training data for DQN. Okay. So, yeah, for example, you see that experience replay memory is invoked at a time step 1, S6 is selected as the initial state. So, now the current neural network is invoked. So, based on the Q values, maybe the Q7 is the highest. Okay, argmax you have to apply. So, the corresponding action is A7. Select the epsilon greedy action. So, now this A7, so A7 is used, okay. So, A7 is given to the environmental simulator. So, then it shows that based on the what was the initial state? Initial state was S6, and if the A7 is the action, then the next state will be S4 and the reward will be R5, and that is coming from the environmental simulator. So, this tuple S6 is the current state, A7 is the action, R5 is the reward, and S4 is the next state. This is now added in the training data. Okay. So, you can see that this way we are generating the training data. Okay. So, these are some batch of random samples. Next, maybe it can use the S27. Again, it can use the Q neural network to identify the Q values of all the actions given S27 as the state, and then it can find out the highest action which is having the highest Q value. So, and then okay, you understood that this way this memory is calculated. So, now okay, so this way this training data is generated. Now you have to train using this training data. So, suppose this is your first sample in the training data. So, again the S1 is used here. So, now you know that A4 is the action. A4 should be your output, like Q4 dash should be your highest Q value. So, yeah, so this is the thing that it should Q4 dash. So, Q network outputs the predicted Q value, okay. Yeah, and you know that the next state is basically S2. So, this S2 is given to the target neural network. From the target neural network, we are approximating the Q values for the S2 because S2 is the next state. So, we are approximating the Q values for the target for the next state S2. So, you know that maybe Q9 is having the highest Q value. So, now you calculate the temporal difference formula. So, what is the target Q value? R1 is the immediate reward plus gamma into max Q value of the S2. No, S2 is the next state, and this target neural network is giving us the Q value of the next state. So you know that this Q9, so we are getting the Q9 and gamma is the discount factor. So we are applying this. So R1 we can get from the training data. So this is our target Q value. So now you calculate this. So you now calculate the loss. So what is the loss? So this Q4 dash is your what? Previous Q value. And now you have approximated the future Q value. So that one predicted Q value and the target Q value. Got it? So that is the temporal difference formula. So that is the loss. MSE of predicted Q value and the target Q value. So Q4 dash is our, you know, the predicted Q value, and R1 plus this is our, you know, the target Q value. So this loss we are calculating. So and this loss we are back propagating, and that way, you know, we are basically we are updating the this Q network. Okay, we are not updating the target network, we are updating this Q network. Okay, by using this loss we are updating this Q network. Okay, we are updating the weights. So you can see the initially the both the networks have the same weight. Here also we are having W1, here also we are having W1. Okay, both the networks are having the same weight, but now you will see gradually. So now we are updating this Q network. So this is now we have updated the Q network. So here it is having the updated weight. This is the W2. Okay, so after time step T, you see it is having a WT. Okay, and after some time step, what you have to do is that you have to copy this weight here also, target neural network. You have to copy WT after some time steps. Okay, you have to also copy the Q network weight to target neural network. Okay, so now let us see the pseudocode. So this is the deep Q learning with the experience replay. So initialize the replay memory D with capacity D. Capacity means how many samples you can store in the memory. Initialize the action value function Q with random weights theta. Initialize the target action value function Q with weights. So yeah, so initialization are same. So the same parameters are used for the, you know, the target network and also the original network. So in episodes 1 to M, so you can initialize the sequence and the preprocessed sequences. So with probability epsilon, select a random action AT. So yeah, so you can select, we are selecting a random action. So we are starting with any state. Execute action A in emulator and observe the reward and the next state. Okay. Yeah, and then that we are adding in the replay memory. This tuple we are adding in replay memory. So now you select some transitions from the D, and then this is the thing. So we are updating. So Yj equal to Rj. Otherwise, this is the thing. So if this is a terminal, then only the immediate, because then there is no future future state. Otherwise, this way we are updating the Yj, and this is the difference. This is the you know predicted, and this is the this is the estimated. This is the predicted, and this is the estimated, and this is the temporal difference formula. Okay. And you have to use a gradient descent on this, and you have to apply the gradient descent on this to update the parameters of the theta. Okay, so this is the deep Q network. Yeah.
The probability for exploration exploitation trade-off epsilon, is that empirically assigned, or is it learned as well?
Which one?
Ma'am, in the first form with probability epsilon.
This one? Yeah, you have to select. Yeah, that is also a kind of parameter. Yeah. So clear. This deep Q learning with experience replay. Yeah, and this is important. See what I told you, that after some C steps, you have to update the target network with the original network's parameters. So Q dash equal to Q. Q dash is your target network. Q dash is equal to Q. Clear now? So yeah, so now let us see some applications. So Akash, food is ready? Huh? Are you sure or not? Okay, so let me show you just one application. So task-oriented dialogue systems and the open-ended dialogue system. So you know, the task-oriented dialogue system means that you have a task in hand. Like you know that you ask your dialogue system or chatbot to solve a particular task. Like you give Alexa a particular task. And chit chat means you as a friend. Suppose there is a chatbot who is simply behaving as a friend, you know, and this kind of chatbots are becoming very popular nowadays. Like some counselor, like you know, mental health counselor, because you know that there is in Indian setting there is a stigma. We do not generally, if we are suffering from some mental health issues, we do not want to go to a doctor. So if there is some kind of, you know, first point of contact who can simply understand your problem, the problems that you are suffering from. Yeah, so chit chat means that it will simply discuss with you on some particular problem, try to understand your issues and etc. Yeah, so that is called the open-ended dialogue system. There is no task in hand, but it is more difficult because in that case you have to keep the customer engaged, you know, because task-oriented dialogue system design is very easy because user has assigned you a particular task and the chatbot has to solve that particular task, like maybe booking a restaurant or booking a flight ticket, or maybe the computer is not working, so you have to give a solution for that. That is the only task. But suppose the customer is only interested in talking, but you have to keep on talking, no, on a particular topic, and the customer should not feel disconnected. So there are many other issues, like you have to think about the sentiment, emotional aspects of that particular customer. So there are many issues. Yeah, so let me show you. This I already discussed with you. So yeah, so this is the work that I mentioned that we are doing with the Accenture. So in case of this sales agent, so we are trying to develop a agent or a chatbot which can sell a product. Okay. So for example, user is saying, "Hi, can you help me in buying a mobile?" Sure. What kind of features do you want in your phone? User is saying it should have 32 GB internal RAM and at least 13 MP camera quality. Agent, is that all features that you need? And color should be gold. So it now make a search in the database and there is a match. Congrats, there is a perfect phone for you. You should buy this. No, I do not like this color. I want something in this color. So now user is not happy with the color and it is a multimodal. So user can also express something in the image form. So maybe user is not aware of the color of this, rose gold color user is not aware of. So user is showing the image and user is asking that I need something in this color. So the, the agent has to extract the color name from the image. So no, I do not like this color. Yeah. So agent, can you please confirm that you phone in rose gold color? Yes, you are right. I love this color. Then surely you will like this. So now it is giving an alternative option. So this situation is called the dynamic goal change. So initially user has given a specification. Accordingly, there is a goal. Okay. So in many cases, there is a user has specified a goal. Now there is during the conversation, there is a dynamic goal change. Okay. So maybe you know that somehow because maybe either the product is not available or user has changed his mind. There could be many different reasons because of which there is a change in the goal. So this situation is very common when you are designing a dialogue system, and this is called the dynamic goal change. Okay. And you have to handle that. So here this has happened.
The inventory how is the chatbot determining inventory? Is it represented in some form of vector DB and then
So it is in this case we assume that there is a database, and it is a kind of dynamic database. Just keep on updated. Like what happens, no? Like shopkeeper is also maintaining a database, no? All the products that there is a obviously they used to have a database. So there is a background database, and all the products which are available are mentioned there. So it has to keep on search there.
Also, how does it interact? Is it more of like a vectorial representation or standard SQL?
SQL.
Chatbot,
Yeah.
generate SQL queries?
Yeah, SQL queries and then making a search. It is a SQL based query. Yeah, so yes, it is nice. How much does it cost? So it costs 350 euro. Oh, it's too costly for me. I need a phone within 250 euro. No issue. So it is again, showing it a some alternative phone. Okay, because the user is not happy with the cost, it is showing an alternative phone. So it's really cool. Please book it this. So you can see that so many changes in the goal. Okay, initially there was a goal, user doesn't like the color, there is a change in the goal, then again there is a change in the goal because of the price. So there are so many, the changes. Okay, so I think we have to stop because you have food, and then also you need to, yesterday also we could not show you the demo. So today there is some good demo on this prompt engineering of the LLMs, because Sandeepan discussed these large language models. So students will show you how to make a prompts of these large language models. Yeah, so I will please go through this. Like if you are interested, please read this our paper. Okay, this is a IJCNN paper of us. So where we discuss the data set. This data set is also available, and this is a Accenture project. We are still working with Accenture, and so the data set also we made public, and we developed a dialogue manager. So our main contribution is this dialogue manager. And this dialogue manager is the capable of handling so many things, like there is this image part. So from the image it can extract some features, and then this dynamic goal change, like when to change the goal, like it has the capability of dynamic goal change. And then as I mentioned that persuasion, like it has to persuade the user to buy some alternative product, or there is also negotiation capability. Like I have not shown this in this example, but maybe there will be bargaining, okay, finally on the price. The customer wants to buy in less price, so there will be some kind of negotiation. So those kind of capabilities are there in the sales agent, okay, because this dialogue system is a very what should I say, very hot research area now, where you can do lot of applications of reinforcement learning, because reinforcement learning is required because you can only give feedback that your response is not good, your response is not bad. So it is not you are making the user sentiment negative. So that's why sentiment also is measured, because when it is a sales bot, it's very important that customer should be always happy. No, we cannot hurt the sentiment of the user. So it's also important that the chatbot cannot generate a negatively it cannot hurt the sentiment of the user. So that's why there was a sentiment based reward also. So yeah, so just go through this paper, and I will discuss maybe in the tomorrow's that also I have a lecture. I will discuss about this.